Hey class, so today is going to be a first of many videos that we're going to be watching about Chapter 8, the first one being about L'Hopital's rule. So the goal is that on several days you will have a video as your homework, so you'll watch the video, take notes on the video, and then come to class the next day prepared to work on problems from the video. That way you can really use your class time to learn and get help and practice together as opposed to trying to do it all by yourself at home. So that is the goal. This is where we're headed. So this is the first video, again, section 8.1. So this homework that you see right here will be something that, again, all homework is due on the day of a quiz, but you don't need to do this tonight at all and have to start it tonight. You can even work on it in class tomorrow. Okay, here we go. So we're going to be talking about limits a lot in the next couple chapters. And so we're just doing a quick review. At least the first one is a review. So we want to know the limit as x approaches 0 of sine of 5x over 3x. Well, back in pre-calc, you would have learned that sine of x over x, the limit as x approaches 0 of this function, was equal to 1, this limit. So in this particular problem that you see here, we have sine of 5x, but we don't have 5x in the denominator. So the way to simplify this or make this work is you're going to multiply the denominator by 5 so that it matches. So you have a 5x and a 5x. But whatever you do the denominator, you have to do the numerator. So now you can see, hopefully this looks familiar to everyone, that this little portion of the problem, sine of 5x over 5x, that limit goes to 1. And you are left with 5/3, which is the answer to this problem. The next problem isn't quite so easy to evaluate. It does turn out that this one is also equal to 5/3, but you don't really have the skills to do this one yet. So you'll come back and visit this problem later on using the technique that you're going to learn. So the technique that you're learning is called L'Hopital's rule. And basically what's happening is you're trying to evaluate this limit right here, the limit as x goes to a of f of x over g of x. And the situation that's occurring is that the numerator is equal to 0 and the denominator is equal to 0, which this should sound familiar because last year we would have called this an indeterminate form. And most of them last year you would have been able to factor and reduce. This is not going to be the case here. So what you're going to do is use calculus. So if this is what's happening with it equal to 0, if you can take the derivative of both the numerator and the denominator, and the denominator's value is not equal to 0 when you substitute that a in, then that becomes the actual limit of the problem. So take the derivative of the numerator, take the derivative of the denominator, substitute that a value in, and this is your limit. So we're going to do several problems like this. So here's the first one. Cosine cubed of x over 2 divided by sine of x. And if you were to substitute pi in for x, you get cosine of pi over 2, which is 0, sine of pi, which is 0. You have to check first to make sure that it's 0 over 0. Otherwise, you can't apply L'Hopital's rule. It has to look like that. So you're going to take the derivative of the numerator and the derivative of the denominator. So the derivative of the numerator using chain rule becomes 3 cosine squared x over 2 times a half. And the denominator is equal to cosine of x. So we're still substituting the same value in, so cosine of pi is equal to -1. So already I don't have 0 on the denominator, so that's good news. And then here, when I substitute pi in here, cosine of pi over 2, we know the whole thing equals 0. So I have 0 over -1, which gives me a limit of 0 for this problem. All right, so we're going to continue down this path. But the first thing I'd like you to understand is really that they have 4 possible situations. And the first one was when you have 0 over 0. We just did that. That's pretty typical. We did that last year. So if that occurs, or if you have infinity over infinity, both of those are really going to behave in the same way as each other. We call that case 1. And you just use L'Hopital's rule as is. So a derivative of the numerator over the derivative of the denominator. These remaining 3 things over here are 3 different situations, and what you're going to do with each of these is rewrite or revamp the problem so that it looks like 0 over 0 or infinity over infinity. So it has to become a fraction. So case 2, if you're multiplying two things together, one of them is infinity and the other part is 0, then you need to do some sort of change to the problem to create it, the infinity part, to make it 1 over 0, so that you're then creating case 1, okay? Case 3 is when you're subtracting two things from each other and they're both infinities. In this situation, you're going to create one common denominator, and usually that'll create case 1 as well. And then finally, if you have something that is a power, so 1 to infinity, 0 to 0, or infinity to 0, and we're going to have a special case of this where you're going to use logarithms, kind of like logarithmic differentiation we did back in first semester, and then that'll turn it into case 1. Okay, here we go. So example 1 is the limit as x goes to 0 of sine of x over x. Okay, so this one we already know, we've done this problem, you know that this is supposed to be 1. But if you're not sure of it, you don't remember, then because you put 0 in for sine, you get 0, and 0 in for x, you get 0. So this is 0 over 0. You could then apply L'Hopital's rule to this problem. You don't have to even remember the limit. And when you do that, you end up with cosine x over 1. Cosine of 0 is 1. So the whole problem has a limit of 1. So done deal. Okay, we're going to move to the problem to the right. So now I have the same type of problem you would have had last year, where you have something that we would have factored and reduced. And you can still do that problem this way, or this problem that way, I should say. But this will work really well with calculus. So I take the derivative of the numerator, take the derivative of the denominator. So this derivative is 2x, this derivative is 1. Substitute the 2, excuse me, and you get 4. So new method, old method. Okay, this problem down here, the limit as you approach pi over 2 of secant x over 1 plus tangent x, back in the day, you would have tried to do something with some sort of trig manipulation where maybe you would have multiplied by, secant or 1 minus tangent or something like that. But now all you have to do is use L'Hopital's rule. So you take the derivative of the numerator and the derivative of the denominator. So the derivative of secant is secant x tangent x. And the derivative of 1 is 0, and the derivative of tangent is secant squared. Cancel out the secants, and you have tangent over secant. And now you have to rewrite this really in a different form, so that way you can take the limit. So I changed tangent, into sine over cosine, and secant into 1 over cosine. Reduce, and you're left with sine. And now you're substituting pi over 2 in, and you just get 1 as your answer. Please make sure you're pausing the video if you ever need to so you can get the information you need. All right, last problem in case 1. Derivative of natural log of x is 1 over x. Derivative of x is 1. The limit as x goes to infinity, so 1 over infinity, is really just equal to 0. So I was able to solve 4 problems with using L'Hopital's rule. Okay, here's a case 2/3 situation. So this is a multiplication problem. When you substitute 0 in, you get 0 here, and then this, as you approach 0 from the right, is going to negative infinity. So it's multiplying things together. So here's how you're going to revamp the situation. So you're going to rewrite the problem so it's a fraction. It's a fraction over a fraction, or something over a fraction. So in this case, I chose to do natural log of x in the numerator and turned just the x part into 1 over x. And now I have something that's infinity over infinity. So then I can take the derivative of the numerator and the derivative of the denominator. So natural log of x is 1 over x. 1 over x becomes negative 1 over x squared. Flip and multiply, substitute 0 in, and you get 0. This method works great on this side. If you try and rewrite it as this fraction, the one on the right-hand side, it becomes a big, humongous mess. So I'm not even going to show it to you because it just looks ugly. Feel free to try it if you like, but it's a big, huge mess. Okay, 2 more case 2 and 3 problems, which I am going to just show you the work. And what I want you to do is pause the video and look at how I did the problems so that you can solve the problems on your own. Okay, here's a case 4 situation, and this is going to need the chunk of time here to understand. So this is a power problem that's raised to a power of x, and the x is infinity. So you end up, this is actually 1 to infinity is what we get. So we're going to use kind of like logarithmic differentiation to do this. So the first thing that you want to do is set the limit part, the whole thing, you're going to set it equal to y. Okay, so we're just going to make it be like an equation. So y equals the limit as x goes to infinity of 1 plus 1 over x to the x. Okay, and now we're going to use logs. So we're going to treat this as an equation, and we're going to take the natural log of the left side and the natural log of the right side. And when we do that, we use log rules and we pull the x out front. So now I have the limit, and you're kind of ignoring the limit for right now, of x times natural log of 1 plus 1 over x. If it helps you to rewrite this expression as one fraction, you can do so, but I'm actually going to take this multiplication problem and turn the x into a fraction in the denominator. So kind of like what we did a couple problems ago. I wrote it as x to the negative 1 because I know I'm going to have to take the derivative of it, but it's really like writing as 1 over x. I haven't done anything yet with L'Hopital's rule. I'm just rewriting it in a form that L'Hopital's rule can be applied to. Okay, so now I'm going to take the derivative of the numerator and the derivative of the denominator. So derivative of the numerator is a kind of a big mess. So I'm going to just leave that like that and see if you can figure out what I did. I actually kind of skipped a step in the middle because I took the derivative of the numerator and the denominator and did some reducing. So see if you can figure out what I did to reduce. But once you get to here, this is something that is no longer 0 over 0 or infinity over infinity. So now you can substitute your infinity in down here for the x. And you end up with, you end up with 1 over 1 plus 1 over x, which just that whole thing's limit is equal to 1. Okay, so now I have gotten rid of the whole entire limit thing. I have the natural log of y equals 1. Which now I'm going to undo the logs, because remember I didn't have logs in the problem, so I'm going to undo the logs to figure out what y is equal to. So this really means that y is equal to e. And remember that y was originally equal to this limit problem that I started off with. So therefore, this limit, this whole entire thing, is equal to e. This thing here that we just found is actually the definition of what e is equal to. So this is a mathematical equation or a mathematical expression that we use to stand for e. Okay, one more problem that I'm going to show you the work for. So I'm going to pull out the steps, but I'm not going to talk. I'm just going to pull them out. And then feel free to stop the video as you need to understand the material. So the limit as x approaches 0 from the right of x to the x power is equal to 1.